A region in the form of an equilateral triangle of height L has a uniform magnetic field B pointing in plus Z direction. A connecting loop PQR in the form of an equilateral triangle of the same height L is placed in the XY plane with its vertex P at x equal to 0 in the orientation shown in the figure. So in this question there is a magnetic field in this region. It is pointing upwards. So there is a magnetic field in this region and it is pointing upwards. PQR is a coil. This is a coil PQR. And this coil is moving downwards with a velocity v, it's given. And at t equal to 0, the loop starts entering the region of the magnetic field with a uniform velocity v along the plus x direction. So plus x direction, okay, it's given in the figure itself that this v is in this direction, x direction. So it is shown here, this is x direction. Okay. The plane of the loop and its orientation remain unchanged throughout its motion. Which of the following graphs best depicts the variation of the induced EMF in the loop as a function of the distance x starting from x equal to 0? So there are 4 graphs shown here. So we have to decide which of these 4 will correctly give the relation between EMF and x. Okay, so this is the question. In this question we'll be needing the area of an equilateral triangle, the formula for area of an equilateral triangle in terms of its height. So suppose we have an equilateral triangle as shown here and its height is L. Since this angle is 60 degree, the half of this will be 30 degree. This side, this will be L by root 3, as we know that perpendicular, this side is perpendicular for this triangle. So perpendicular over base, this is tan 30 and it should come out 1 by root 3. So therefore this is L by root 3. And total distance, total base length will be 2L by root 3, the twice of it. This total distance, 2L by root 3. So area is half base into height. So it is L square by root 3 and we'll be using this formula later on. So please remember this formula. Area is L square by root 3 and we'll be using it. Okay, the situation is this. This white triangle is the loop which will move and this red triangle is showing the area of magnetic field. So in this red triangle there is a magnetic field present. So first I'm considering motion x which is less than L, like this. So it is less than L and it has moved by a distance x. This distance is x and this x is less than L. L is this total distance. So I'm taking this case first. X is less than L and this yellow line is actually line of symmetry. So there is a symmetrical situation about this yellow line and therefore these two triangles will be congruent and the total distance x will be equally divided x by 2 in each of these two triangles. This area of this triangle, as we have derived just now, it is height is square, height is x by 2, so height is square upon root 3. We have just derived this formula. So area of this triangle is this much and since there are two triangles in it, so total area of this coil which is inside the magnetic field, so this area which has entered into the magnetic field, so this area will be twice of this total area and if we multiply by B, we'll get flux, so B into area, and the EMF is minus d phi by dt, as we know. So EMF is minus B d phi by dt, and this is the expression for phi, and if you differentiate this, you'll get this result, and dx by dt is obviously V. Okay, so this is the expression for EMF. This is the expression of EMF when x is less than L. Okay, what happens when x is more than L? Again, I'm taking this situation again, and now the coil is moving by a distance x, which is more than L, like this. So it has moved a distance more than L. See, this is the position of vertex initially. So from this position, it has moved all the way down to this position. So the distance moved is x, and which is more than L. L is the height of this triangle given in the question. Okay, so this distance, obviously, if we denote it by delta, it will be x minus L. You can verify. Uh, these two triangles are in fact congruent triangles, this side and this side. These are the heights in these triangles. They'll be equal. It's called m each. Suppose I'm taking the height as m. See, if we have two line segments of equal size, and suppose the perpendicular drop from one end falls on the end of another line, and if we draw two more lines like this, making equal angles with the lines, these two angles are equal, then obviously we have a situation here when these two triangles formed, these will be congruent triangles. You can easily verify. So these two are congruent triangles. I'm just redrawing this diagram with a different scale so that it fits here. It fits here so that you can verify the same situation is here. So these two triangles are similar triangles, and therefore we have taken the same heights as m. Okay, and there is a line of symmetry always. So here, this is the line of symmetry. So this is a central line. This line is central line, and therefore this is half of the distance, total distance moved, that is x by 2. There is always a symmetrical line in every position. Suppose this loop advances a bit further and situation is like this. Even then there is a central line. Even then there is a line which is a line of symmetry. So this line is line of symmetry. So in every position there is a line of symmetry, and the triangles formed here and here will be congruent. So you can verify m. This m is total L minus x by 2. This is x by 2. This is total L. So L minus x by 2 is this m. So m is L minus x by 2. And if we differentiate dm by dt, L is a constant, so it is simply minus v by 2. Similarly, if we see delta, delta is this distance, which is x minus L. And if we differentiate this, we'll get d by dt of delta equal to v. Dx by dt is v, and L is constant. Okay, so here area means the area of the coil, that part of the coil which is inside the magnetic field. I mean, in this part there is a magnetic field in this part. So this area will have flux, this much. This area will have flux. So we have to find this area. So how to find this area? This is actually total area of all this. This is total area of this loop, this total area. So this total area is L square by root 3. We've just seen the formula to find the area of triangle. Height is square by root 3. Okay, then we have to subtract area of this yellow triangle, area of these red triangles, two red triangles. So The height of yellow triangle is delta. So therefore delta is square by root 3. This we have subtracted. And so there are two red triangles. So area combined is 2 times m square by root 3. So this is the area having flux in the region of magnetic field. So I'm simply differentiating this relation. 1 by root 3 is a constant, L square is a constant, minus delta square, so it is minus 2 delta into d by dt of delta, which is V here. Then the differentiation of this term is minus 4m into dm by dt, and dm by dt is minus V by 2. So there are two negatives which make it a positive here, 4m V by 2. Then I'm simply putting the value of delta as x minus L. M, the value of m is L minus x by 2 from here. And this is the expression for dA by dt. Then the EMF is, we know that EMF is minus B times dA by dt. So it's simply minus B times dA by dt. So this is the expression for EMF, and solve it. So finally we get the expression of EMF as this. So now we have two expressions. One was the expression we had earlier, and so that was the expression found here. And this was the expression for x less than L, while just now we have seen this expression for EMF when x is more than L. So now we have two expressions for EMFs when x is less than L, and this is the expression when x is more than L. We have to graph these two. So this is the graph. You can now verify. When x is 0, EMF is 0. So the graph is from origin. It is starting from origin. When x is approaching L, so this value will go to this value, minus BLV by root 3, when x is equal to L here. So since it is linearly varying with x, so it's a straight line graph. So this is a straight line graph from here to here. It's a straight line graph. This part is also a straight line. If we put x equal to L in this part, so it will be BV by root 3 minus 4L plus 3, and in place of x there is the value is L, suppose. Then it solves to BVL by root 3 with a minus sign. It means value of this graph at x equal to L is equal to this value. So it is, there is a continuity. It means they approach to same value at x equal to L. This EMF is equal to 0 when this part is 0, and this part is 0 when x is equal to 4L by 3. So that is at x equal to 4L by 3, this is 0. And at x equal to 2L, this will be equal to this value, 2BLV by root 3. You can verify. Put x equal to 2L and solve. So the second part of the graph, it moves from here to here. Okay, thank you.